All right, let's do this. So, today's topic. It is. Now, today's topic is recursion. This is the introduction this semester of a new problem-solving strategy. So it's pretty cool, actually. I think that, again, when I look back on my own computer science education 20 years ago now, I don't remember a lot from taking my first few computer science courses. I remember liking it, obviously. It's one of the reasons I'm here. But I do remember recursion. I remember being introduced to it. I remember being confused by it. I remember being just weirded out. It's like, what? It's like you start with this mental model about methods calling other methods, and suddenly a method's calling itself, and you're like, what is happening? And so I get that. I think, for some, this is a topic also, I think that's a little polarizing in the sense that, some of you with potentially stronger math backgrounds may be more prepared for thinking about problems in this way. Some of you that came into the class with less programming experience, who have been steeped in our way of solving problems and our approach to things since day one, may find recursion a little bit more mysterious at first. But the best way to master this topic, like anything else we do, is just to spend a fair amount of time practicing. So that's what we're going to do today. Please throw questions up in the chat. As always, I love to answer questions, and I'd rather do that than just sort of go through a précis of the material that's already up in today's lesson. And so as we introduce recursion, we, as this is a new problem-solving strategy, we now need a term to describe the way we've been doing things in the past. And so, the problem-solving strategy that we've been pursuing up until this point is something known as iteration. So, when we look back and we think, okay, how have we been solving problems? How have our algorithms been working? Typically, they've been repeating a series of steps, and repeating those series of steps using a loop. That has been one of our core sort of programming constructs, right? So very beginning of the class, we introduce decision-making constructs like if statements, looping constructs like for and while and do while and things like that. And those have been the tools that we've had in our toolbox, and that's how we've been attacking problems. Starting today, and particularly starting tomorrow when we start talking about trees, we're going to really need recursion, this new way, this new approach, as a complementary set of techniques to the ones that we've already been using that in some cases can lead to much more elegant problem-solving strategies. And so we could do, if you guys want, we could probably do a couple of different examples of this. And actually that might be a fun thing to do today. If you want, is to queue up a couple of algorithms that we've previously implemented iteratively and try to implement them recursively and kind of look at the difference. So the first one that we did today is this palindrome example, right? So I'm trying to determine if a string is a palindrome. A palindrome is a string that has the same characters forwards and backwards. Now, if you look online, there are some definitions of palindrome that relax things like, for example, they ignore white space or whatever. And our definition, the one that we're implementing, is stricter than that. It requires that the strings literally have the exactly same characters forward and backwards. The fun thing about ignoring spaces is that it allows you to introduce some more interesting palindromes, basically. But our definition of palindrome is literally that the string has the same characters forwards and backwards. And so in the walkthrough, we do this twice. We design two solutions of this problem. They are completely equivalent to each other in the sense that if I gave you, you can think of performing this experiment, right? If I just had this algorithm implemented somewhere and you could use it, there's no way that you would be able to determine by trying different inputs that one approach was iterative and one approach was recursive, because they're completely equivalent to each other. Given the same inputs, they produce the exactly same output. And so they're both solutions to the problem, but they're quite different. So here's looking at our first approach to doing this, which uses a loop, uses iteration. We do some input validation. We handle this sort of special case where the string is either empty or one character. We consider a single character string to be a palindrome. Empty string we also consider to be a palindrome. I don't know if that's, I think that's true. I think I would probably argue that. But, I'm not sure. I don't know about the International Society of Palindromes and how they would feel about this. But anyway, and so then, again, what characterizes this iterative approach is the loop. You see a for loop. That is our iterative programming construct, in the sense that we're repeating a series of steps over and over. In this case, what we're doing is we're scanning the string, and we're starting at the front and at the back, and we're looking at the pairs of characters that make up the string. So essentially, if you imagine this one, we'd be looking at A and then A. That's the first character and the last character, and making sure they're the same. And then we move in one character. So then we look at B from the front, we move one forward. From the back, we move one toward the front. Look at those two characters. Are they the same? Continue that until we get to, until one of two things happens. Either we find a character that doesn't match the character that it should. So, if the character at a particular position at the front and the back of the string aren't the same, then we can immediately conclude that the string is not a palindrome. So this is one of these examples where we're sort of proving by contradiction. As soon as we find a mismatched pair of characters, we're done. We can just stop. If we get all the way through the string and we haven't found any characters that are mismatched, then it's a palindrome. We're done. And so, this is, I'm trying to think, we implemented, we talked about this pattern before, right? Where it's essentially, for example, if I'm trying to determine if every number in an array is odd, I might say, okay, I'll go through, and if I find a number that's even, the whole array is not odd. And so I return false inside the loop. If I drop out of the loop, that means I've checked every single character I need to check, starting at the front and the back, moving to the forward. This loop, if you look at the loop condition here, it walks front up until input.length divided by 2. And in the walkthrough, I sort of talk about that. That turns out to skip the middle character of an odd length string, but that's fine because that character cannot affect whether or not the string is a palindrome. So for example, this string here, ABA, you can replace B with any character and the string is still a palindrome, right? That middle character in an odd string plays no role, and so we skip it in this loop. We don't have to. We could walk it one farther in. I mean, you can actually walk both of them across each other, right? So I could have this loop go all the way from front is 0, front is less than input.length. And what would happen is I would end up checking the string twice, right? Because I would start here and I would be walking these things in, and at some point they would cross and then they would keep going until the front got to the end of the string, at which point the end would be at the front of the string. But doing that means that I'm double checking a bunch of characters that I don't need to. And so to make this slightly more efficient, I've just decided to stop once I get to the middle. Okay, good. Now, let's look at the recursive approach. So recursion, is not something that we expect you to just understand instantly. The principle behind a recursive solution is that we try to make a big problem a little bit smaller. And what we also do is we exploit the fact that the smaller problem is usually similar to the bigger problem. It's just a little smaller. And so, for example, here what we do is we break down the problem of determining whether a string with n characters is a palindrome into two things. The first thing is I look at the first and the last character, right? So that's what I'm doing here. If these two characters aren't the same, so if I give you any string of any length and the first and last character are not the same, the string is not a palindrome. It can't be a palindrome. So I check the first and last character. If the first and last character are not the same, then the string is not a palindrome. And so you'll see my method returns false. If the first and last characters are the same, then what I've done is I've created a smaller problem to solve because I started with a string with n characters. And now I know that it might be a palindrome, but what I need to do at that point is I need to check the string inside the first and last characters. So, if I have a string with, 82 characters, I check the first and last. What I have left to check is a string with 80 characters. And so what I do, and this is what characterizes, or at least in this class, what's going to characterize our recursive implementations and hence our recursive algorithms, is I just restart the algorithm again on a slightly smaller problem. So I gave you a string with n characters, and now what you're saying is, okay, I've solved a little bit of the problem, but I still have n minus 2 left. And so I need to check that inner string. And all that happens is I start the function again with a different string. So if I started this, and what we did here is, and I can run this. So we essentially printed the input as it went. And what you see is the first time that is palindrome recursive is called, it's called on the string ABCD, DCBA. The next time it's called on the string BCD, DCB. The next time it's called on the string CD, DC, and then finally on the string DD, and then finally on the string empty. So in order for a recursive solution to work, if we're going to make the problem smaller and smaller and smaller and smaller, at some point there has to be a problem that's so small that I can solve it right away. And so what you see here is, this if statement on line 7 is handling this smallest subproblem. So what this does is it says, if you've asked me to check a string that's either empty or has one character, I'm done. I know that string is a palindrome, and so I'll just return true. And so what the recursive solution is doing is it's basically making the problem smaller and smaller and smaller and smaller and smaller and smaller and smaller at every step. You can imagine that string starting out bigger and then getting whittled down character by character by character by character by character until I get to the point where I can solve the puzzle. And so this is sometimes known as the base case. This is the smallest instance of the problem that I can solve immediately. This is known as the recursive step. This is when I restart my algorithm on a smaller instance of the problem. And so let me clear out some of the cruft here, just the extra print statements. Well, actually, I think we did this. Well, I'll just do this here. And so if you look at these two solutions, like I said, they are completely 100% equivalent to each other. They produce the same inputs given the same output given the same input. Therefore, they're the same. They're equivalent. But they are very different, right? Here we see one of the hallmarks of an iterative solution, which is a loop. Here we see the hallmark of a recursive solution, which is a method calling itself. Because when we use a recursive approach, we're going to make the problem smaller, but that smaller problem is still an instance of the same problem we were solving when we started. Maybe that's the important thing to realize, particularly with the type of recursive problems that we're going to work on. Recursion exploits this fact that there's a symmetry here, right? In the sense that I can construct the problem of determining whether or not the string is a palindrome to checking the first and last character and then determining whether or not that smaller string that's inside those two characters is itself a palindrome. And if I repeat that process enough, eventually I get to a string that's so small that I'm going to solve it right away. All right, questions at this point. This is, like I said, I'd be happy to, to walk through these more carefully. We can also go ahead and do some other examples where we take iterative solutions that we've constructed in the past and produce their recursive equivalent. One of the things I point out when we talk about the definition of recursion in this particular lesson is that recursion and iteration are completely complementary problem-solving strategies. One is not better than the other. There are straightforward ways to essentially take recursive solutions and make them iterative. And then also frequently to take iterative solutions and make them recursive. And so there are kind of standard transforms that you can use to kind of map between the two spaces. There are no problems that recursion can solve that you can't solve with an iterative approach, and there are no problems that iteration can solve that you can't solve with a recursive approach. And in fact, there are entire programming languages. One of the ones that was mentioned in Wikipedia was a language called Clojure, where there are no looping constructs at all. Clojure does not have, and this is true of some other languages that are referred to as functional. They're in a family called functional languages, where there is no loop. There is no way to iterate. You cannot, there is no for loop, there's no while loop, there's no looping constructs, period. Those languages people use to solve real problems. And so essentially, that's sort of an existence proof of the fact that we can use recursion to solve any problem. Now, there are times when recursive solutions are not, in my opinion, the most elegant solution to a particular problem. There's also times when iterative solutions are not the most elegant or the most appropriate to a particular problem. But they are completely complementary approaches. All right, I'm gonna pause here to let some questions emerge and see what you guys are curious about doing today. That's kind of, this is not, I wouldn't argue that this is a big lesson in terms of content, but this is a very new idea, particularly for people that haven't been exposed to this way of thinking before. And so, we're going to spend a fair amount of time over the next, you'll get regular practice with recursion from now until the end of the semester. It's not going to be our sole focus. We'll do some other topics, but even the other topics that we look at frequently allow us to experiment with recursion and to see it applied in other contexts. All right, questions? Maybe there are no questions today. People just want to enjoy the warm fall day. That's also fine. We have recursion on the MP? No. No, there's no real appropriate place to use recursion on the MP. Not that I can think of. Yeah, no. I mean, there's not a lot of iteration on the MP either. But yeah, so the bulk. This has always been true, actually. I mean, the bulk of the practice that you're going to get on the on recursion is going to be through the homework problem. So starting today, tomorrow we'll start talking about trees. Trees are a fantastic data structure for recursion because trees are one of the places that make iteration very difficult. Can you iterate over trees? Yeah. Are we going to show you how to do that for a while? No. Is it a good way to do things? No. So trees are a great place to do this. One of the things to keep in mind with the MP, obviously, is that the MP's goal is really not algorithmic problem-solving development. The goal of the MP is to give you experience working with a larger code base, to give you experience with things like reading documentation, some of the core components of a fairly realistic modern application in terms of a backend component, web API requests and things like that. These are, the MP is supposed to be complementary to the homework problems, right? You notice we don't have any homework problems on networking and API requests as well. Those are kind of hard to write. The MP is a good context to do that. The homework problems will focus more on sort of algorithmic thinking and that sort of thing. It's a good question though. I mean, there are, I will confess that I am not someone who would consider themselves to be a recursion first problem solver. I'm an iteration first problem solver. And so I don't always see opportunities to use recursion. There probably are, and you're welcome to do so. I mean, there's no way to tell, right? That's the whole point. I mean, recursion is a problem solving technique. It's not something that you should do to do it. I mean, you will find problems in your life as a computer scientist where you will be like, wow, there's a great recursive solution to this. And when you find those problems, you should use them. I would say do not ever use recursion to use recursion. People will typically not appreciate that. No, the quiz tomorrow, please check the calendar. Topics are on the calendar. Yeah, we don't introduce something on Monday and quiz you on it on Tuesday. We haven't done that really ever this semester. So yeah, no, recursion will be covered by next week's quiz, and then probably also the quiz after break. We'll have some more recursion, probably more recursion programming problems on that quiz along with some other content. But yeah, no, keep in mind the calendar has the calendar is up to date at this point with all the information about the next few quizzes. So anything you need to know is on there, including the coders chapters and the topic coverage and things like that. Questions? Other questions? Yeah, I mean, I'm trying to think. I hadn't actually. I was having this running joke with a colleague who is very very into recursion, and I was like, I haven't used recursion in 10 years as a programmer, and then like literally the next week, I had this problem where I was like, oh. Yeah, and it worked out quite well. And there's a few other places in some of the code bases that I maintain where we do use it, but yeah, no, lightly, and in places where it makes sense. Good questions. Other questions? Hey. Well, since we're here and we have a few minutes, why don't we do the following? I'll continue to check for questions, but I think for fun, why don't we take a different problem and we'll look at how to solve it recursively. And let's do something straightforward. So we had done in the past, let's call this array search, and I'll take an int values and then int value. And the idea here was I want to return true if the array contains the value and false otherwise. And there's a built-in library method in java.util.arrays to do this, but that's no fun. Let's do it ourselves. Let's start this with an iterative approach. Okay, so we remember how to do this, right? I mean, this is quite straightforward. So I basically say, I'll call this looking for. It's a little bit easier. Values. I say if value equals looking for, I return true. Otherwise, I return false. All right, and now we can say array search iterative, and I could be doing more input validation here, probably should, but I'm not going to. All right, so that's good, and let's make sure this returns false. Good, okay. It's very, very simple stuff, right? We were doing this a month ago, no problem. Characteristics of an iterative approach, I see a loop. Right? I see a loop. And so the question is, how can I implement this recursively? And so one of the things that's kind of fun about recursion is that you have these families of problems, right? And the trick is to think about how do you make a problem that uses a particular type of data structure a little bit smaller. So with the string, we've already seen this with the palindrome. With the string, a lot of times what we do is we make the string smaller, and then we restart the algorithm on that smaller string. With the tree, which we'll talk about tomorrow, the pattern is usually for each node in the tree, we look at its children. So each one of its children, represents the root of a smaller tree, and so that's how we make the problem smaller. With an array, typically what we're going to do is we're going to make the problem smaller by looking at a smaller array. Okay, to do this, I actually am going to have to brush up on my java.util arrays, because what I want is, I want this. Okay, copy of range. And this is going to give me a smaller array. So a copy of range gives me a copy of the array, but it allows me to only copy a portion of it. There are other languages that make this a lot easier to do, like if you use Python, there's a way to do slices with lists that lends itself more to this. Java doesn't really make this as easy as we might like, but we can still do it. So let's try it, okay? Okay, so we're going to say array search recursive. We'll say here's this array, values, int looking for, okay? Now, whenever we write a recursive solution, we want to think, what's the smallest problem here that we should be able to solve immediately? With an array, it's usually pretty simple. The smallest problem is an empty array. The solution to that problem depends on what the algorithm is. In this case, if we're looking for a value in an empty array, we can solve that puzzle right away because we know what the result is. It's false. Okay, so if you ask me to look for any value in an empty array, I'm not going to find it. There's nothing in there. So I'm going to say if values.length is equal to 0, return false. I don't even have to look at looking for. It doesn't matter. I know that this cannot, the array can't contain the value, right? So now what I'm going to do is I'm going to break the problem into two parts. There's the small piece of it that I'm going to solve, and then there's a similar problem that's a little bit smaller than the one that I'm looking at. And so what I'm going to do is I'm going to say if, so I know at this point values isn't empty, which means I know that it has a first element. I'm assuming it's not null. I could check for that, but we're not going to go down that case. It's not super interesting. So here's what I do. I look at the first value. If the first value is equal to what I'm looking for, then I know that the array contains the element. I'm done. So these are both, sort of on some level, well, the first one's a base case, and this is sort of a part of the recursive step. If I find the value, then I'm done. If I don't find the value in the first element, remember, I'm not using a loop here. Then what I need to do is I need to look for the value in the rest of the array. But I also need to make the problem smaller. How do I do that? Well, if the array had n elements, I've checked one of them, but I need to check the other n minus 1. What's out there? Squirrel. Oh, okay. Yeah. Sorry, cat found something outside. So let's go back and look at our arrays. I have this copy of range. So what I'm going to do is I'm going to say otherwise return array search recursive. I'll do arrays.copy of range from 1 until values.length. Oh wait, I need to pass it the array, right? Copy of range, yeah, original. Values 1 values.length, and then also looking for it. I'm still looking for the same value. Okay, let's see what has. Oh, I need to import that. All right, so that also seemed to compile. Now let's see if it works. And then recursive. Cool. Again, same problem, two approaches. The iterative approach, I go one by one using a loop. The recursive approach, on some level, if you think about it, the recursive approach is sort of going one by one as well, except it's not using a loop. It's checking the first value and then calling itself again to check the rest of the array. Let's look at what actually is, so I'll do system.out. There's a nice arrays.toString. That'll give me a nice string value for this array. Values. There we go. And so, excuse me, let's just look at one of these rather than two. So the first time that array search recursive is called, it's called on the full array. I'm looking for through the full array. I check the first value. I didn't find 4 yet. And so now it says, okay, well, I need to check the rest of the array. So it restarts the process on the end. So then I go 2, 5. Check the first value. Not that. Keep going, right? Start it on, look at the array with size 5. Check the first value. Not there. Look at the rest. And that's when I finally get to this point, right? Where I have been asked to search for the value in an empty array, and I know what the result is. So again, 2 examples of the same, these are different algorithms for solving the problem, but they're solving the exactly same problem. Both of these implement an array search. In one case, I'm looping to check every value. In the other case, I'm sort of implementing one of these classic recursive solutions where I make the problem a little bit smaller every time. All right. Runtime benefit from recursion over iteration. No. In fact, it's usually the opposite. So normally, and we don't really go into all the reasons for this in this class because it gets complex, but normally recursive solutions actually produce more overhead than an iterative approach. The reasons for this are, a little bit complicated. So let me provide a caveat here. There are languages that are able to optimize a recursive algorithm or recursive implementation to the point where it approaches the performance of an iterative implementation. Sometimes they can be equivalent. So people that will argue in favor of recursive approaches will typically say, well, the recursive approach is more natural in certain cases, and with an intelligent compiler, you can make it fast enough. And this requires some tricks, right, in your compiler. Let me see if I can explain this in a way that's both sort of compact and accurate. When a method runs, the computer has to set aside memory for all of the variables that the method uses while it executes. So for example, if I have a local variable, like the parameters, for example, to my method, any local variables that the method might declare, those take up space in memory. So when a method calls itself, what happens is let's imagine that, let's just create something called this. That's going to be fine. It's not going to complain. So imagine every time I call array search recursive, I have this variable unused. And every time I call it, I have to find space for that variable. So when I perform a recursive algorithm, what will happen is it'll call itself multiple times. Every time that call is made, the computer has to set aside a little bit more memory for a new copy of unused, because every single copy of that method has its own value unused that's local to it. So if I ran this on a really big array, right, let's say the array had 1024 elements, I would have 1024 copies of this local variable, okay? The iterative solution does not have this problem. And so that's where some of the inefficiencies come in with recursive implementations. Now, one thing you might notice here is in this particular recursive method, the last thing it does is call itself. It's sometimes known as tail recursion, in the sense that there's no code after the recursive step. And so if your compiler is intelligent, it can exploit this. So when the last thing that a method does is the recursive call, an intelligent compiler knows that this local variable will never be used again. It can't be. I'm in the process of returning. There's no code down here, right? So at this point, anything that I've done with this local variable, which I might have needed for a calculation or whatever, its value can be discarded. when a method returns, the values of local variables are discarded. They go out of scope. Remember we talked about scope. They're in the scope of the block of code that constitutes a method. When the method completes, those variables go out of scope. So an intelligent compiler will optimize for this scenario, and it essentially will remove those global variables earlier than it might normally have. And that will allow the memory usage of the recursive solution to be more in line with the memory usage of the iterative solution. There's actually typically a performance. Now again, I should go look at this more, right? Maybe I'm wrong here, but there's typically so there can be a memory usage penalty for recursive solutions. Now again, languages that use this technique heavily typically have a lot of optimization built in. I'm trying to remember. Let's see here. Let's see if Java actually does this properly. Yeah, here we go. So this is tail recursion optimization. Is this? Let's see. So it looks like this was something that is now done in Java 8. This is tail call optimization. So again, the tail call is a function that makes a recursive tail call, means that the last thing it does is call itself. And it looks like oh, okay, I lied. It says Java does not directly support tail call optimization at the compiler level. Now Scala, okay, so this is a sort of a neat point here, right? Scala is another programming language. It's another language that we'll talk a little bit about this later in the semester for fun. Java has spawned a family of languages that are sometimes known as JVM languages. So, and we'll talk a little bit about the history and kind of where this came from. The reason for this is that remember Java compiles to bytecode, and there's this program that runs the bytecode. Well, that program is installed on a lot of computers, right? It might be installed on your computer. You might get those weird notifications that seem to pop up at the most inconvenient moments to upgrade Java or whatever. That program runs what's called Java bytecode. If I can create a language that compiles to Java bytecode, I can run anywhere that Java runs. And better yet, I can use all of Java's libraries. And Java has some very good libraries, and they're also very old, which means they're really well tested and very stable. So there's this family of languages known as JVM languages. Scala is one, Kotlin is another, Clojure, which I mentioned before, that doesn't have looping constructs, is one, Groovy is another. There's at least a few more that I'm forgetting. Those are kind of some of the big ones. These are languages that interoperate with Java, and they run anywhere that Java runs. Scala is a language that is much more functional than Java is. Scala is, and you can go and look at it yourself, and it's a neat language. I haven't used it for a project, but it's, I think it's in a neat space. With Scala, particularly when you look at functional languages, a lot of functional languages make heavy use of recursion. And so they typically have more built-in optimizations for recursion. And so the Scala compiler will detect tail recursion, and it will remove that extra memory overhead that can creep into your program because of tail recursion, because of recursion in general. Java compiler doesn't do this. So again, you see these two different, and maybe they fixed this. This is an old article. I don't know. It says, yeah, it doesn't look like this is something it doesn't look like this has been fixed. Some of these articles are a few years old. I can look up and see a little bit more about what the current state of this is, but so it looks like, again, Java does not optimize for this particular case. Scala does, right? Why the difference? Scala's newer, but Scala is also a language that's much more designed around the use of recursion as a problem-solving strategy. Java's not. Not that you can't do recursion in Java. Clearly we are. We just wrote a recursive method. But Java is a language that's not, where recursion is one thing that you can do among many different ways to approach a problem, rather than languages like Scala, where recursion is really a very core technique that's used in the language. Yeah, it's a good question. yeah, so probably, again, without these compiler optimizations, typically recursive methods will chew up a little bit more memory than their iterative counterparts. The optimizations that you can perform, typically, they don't make the recursive method faster or have it consume less memory. What they'll do is they'll actually just get it back to par, right? So the goal is like, get to the point where my recursive method consumes as much memory as my iterative method. It's usually harder to do better. Good question. Other questions? We have a few more minutes left. Trying to think of, see if there's I wonder if there's a Scala playground online. Or we'll just look up the language since we got started here. Oh, look at their nice page. I wish there was is there a playground here? Oh, here we go. Oh, okay. All right. Does it run? Oh, that's nice, I guess. Yeah, it'd be nice. I don't know anything about Scala, so I'm not going to suddenly be able to do anything with this, but that's fine. It's kind of cool. Yeah, I should check this out though. We could probably add support for it to our playground if we worked carefully. Let's see here. Other questions for today? You edit your own Java compiler to optimize for a given programming pattern. No. Yeah. Well. I don't think so. Yeah. I mean, that would be making the compiler more extensible is not something that I'm aware of has been a big goal for most languages, to be honest. Yeah. So I think in Java the answer is probably no. The compiler is going to do what the compiler is going to do. You don't have a lot of control over that. The one place where you do have a little bit of control, and I don't know how far you could go with this, is that Java has, well, okay, so there's a couple of constraints here. First of all, if you want to use the Java compiler, you've got to write Java, right? So let's say you wanted to add like a new keyword into the Java language or a new construct or something. That's not going to be possible using the standard Java compiler. Now, what people have done is they've written some tools that allow you to take your code and then compile it into Java and then run the Java compiler, right? But now we're getting into sort of esoteric stuff. Java's annotations can also do a little bit of source level transformation on the code before it hits the compiler. If you annotate a method, you can provide, so we talked about annotations in the past, one of the use of annotations can be to allow some code that you wrote to do some manipulation of that code before it gets to the compiler. So you can think of it like there's now an extra stage when you compile your code where it's called an annotation processor. It runs and it gets access to the source code, and it can actually write new source code, which is then compiled. How much can you do with that? Probably a lot, but implementing something like this I think would be difficult. And maybe impossible, but I could look into it. That's a good question. All right, so tomorrow, I'm gonna let you guys go a few minutes early today, so it's a little bit of sunshine out there. Tomorrow what we're gonna do is we're gonna introduce trees, which is a new data structure. It's pretty exciting, and a fantastic place to sharpen our skills with recursion. So really, starting tomorrow, most of the recursive algorithms that we're gonna implement will be implemented on trees. I will look forward to seeing you then. Enjoy. I think today's probably the last day of this really bizarre summer-like weather. So if you haven't been outside yet, please go and get a little bit, the last few hours of it. So I'll see you tomorrow.